Next, we're going to talk about permutations and combinations and how we can use them to determine probabilities. So first let's start with permutations. And the definition of a permutation is that it's an arrangement of objects in a specific order. And the word order is what's really important here. So let's look at an example of a specific set of letters that we're going to try to put in different orders. So we'll start with the letters that spell the word act, A-C-T. And we're going to try to rearrange these letters in as many ways as we possibly can. So we could just leave them in the order they started with, or we could start to rearrange them, maybe leave the A first but reverse the T and the C, or put the T first and then arrange the A and the C, or maybe put the C first and then rearrange the T and the A. So we end up with 6 orderings, which means we have 6 permutations of the letters A, C, and T. So how could we possibly see something like this in a probability problem? We might see something like this particular wording. The letters A, C, and T are placed in a box and drawn randomly without replacement. What is the probability that the resulting word is a real word in the English language? Now keep in mind that probability has a denominator which represents the total number in the sample space, and we can see the 6 elements in the sample space right here. We want to find the ones that spell English words, which would be the word act and the word cat. So of the 6 elements in the sample space, there's 2 that spell real words. So the probability that we order these letters randomly and spell an English word is 2/6 or 1/3. So here's the 6 orderings we just found. There's some specific notation we can use when we're dealing with orderings of objects. Now remember, this is a permutation because we're ordering. And if we want to write notation to represent what we just did, we would write something that looks something like this. So what does this notation mean? Well, the number to the left of the P, and P means permutation, means that we are selecting from a set of 3 objects. That would be the 3 letters we started with. And the number to the right of the P is how many of those 3 objects were we selecting with order, and we were ordering all 3 of the objects. So we have a permutation of 3 objects chosen 3 at a time, which equaled 6. So what would this mean? Well, that would mean that from a set of 3 objects, we're going to select 2 objects with order. So that's a permutation of 3 objects chosen 2 at a time. So how would that work with this set of letters? We started with the letters A, C, and T. How can we choose 2 objects with order? Well, that could mean choosing just the A and the C, or the A and the T, or the T and the A, or the T and the C, or the C and the A, or the C and the T. So the number of ways we can choose 2 objects from a set of 3 objects with order is equal to 6. So let's review a little bit of notation that you might remember from algebra, and that has to do with something called factorials. If you see something that has an exclamation point in it, the exclamation point is a factorial. So 4 factorial means 4 times 3 times 2 times 1. So a factorial is really a product of numbers starting with some value and then decreasing the factors by 1 until our final factor is a 1. So 3 factorial would just be 3 times 2 times 1, or 6. 2 factorial is 2 times 1, or 2. 1 factorial is just 1, and here's the tricky one. 0 factorial is defined to be 1. That's a little surprising. 0 factorial is not 0. 0 factorial is equal to 1. Now here's why that may be important to us. If we want to write a general formula for how to choose R objects from a total of n objects when order matters, we can actually use a formula for that. So, a permutation of R objects chosen from n objects is equal to n factorial divided by n minus r factorial. Now remember, we just tried this. We found out that from a set of 3 objects, if we chose 2 objects with order, we would get a total of 6 objects. And how could we find that using this formula? Well, in this case, n is 3. N is the total number of objects. R is 2. That's the number we're choosing with order. So that would equal 3 factorial over 3 minus 2 factorial. 3 minus 2 is 1, so 3 factorial divided by 1 factorial. Now you have to be careful with this. You can't just cancel the 3 and the 1. You can't cancel the exclamation points. You have to expand these to see what they're equal to. So 3 factorial is 3 times 2 times 1, which is 6. 1 factorial is 1, which is 1. And 6 divided by 1 is 6. So that's exactly what we found by just listing the objects. So let's play with this a little bit. Suppose we want to evaluate this, a permutation of 6 objects chosen 3 at a time. That would equal 6 factorial divided by 6 minus 3 factorial, which is 6 factorial divided by 3 factorial. Now remember, you can't just start canceling things at this point because this represents products. So we have to write the products. And then we can cancel factors if we see the same factor in numerator and denominator. So we do. We see a 3 times a 2 times a 1 in numerator and denominator. So 6 times 5 times 4 is equal to 120. Now there's actually another way to do permutations. And it might be a little more straightforward to you than using the formula, although the formula can be extremely useful as well. So let's say we want to order 3 objects out of 6 objects. And let's actually look at an example of what we could do. Let's say these are the 6 objects and we want to order 3 of the 6 objects, create new sets that just have 3 objects in them. How many of those can we get? So I'd like you to imagine that we have 3 blanks that we're going to fill in with the 3 letters that we are reordering. So if we want to choose something for the first blank, we've got 6 letters to choose from. We could pick any of those 6 letters. Now just imagine that, for example, we'd chosen the D. So once we've chosen the D, once we've chosen a letter from those 6 letters, we only have 5 letters left to choose from for the second letter. Maybe the second letter was the A. It could have been anything. We're just picking the A out for an example. That would leave us with 4 letters to choose from for the third letter. So what do we do with these numbers? There were 6 ways to pick a first letter, then 5 ways to pick a second letter, then 4 ways to pick a third letter. Well, if we multiply those together, we'll get the total number of ways that we can select the 3 objects from the 6. So let's try another problem that involves ordering. Anne, Brad, Chloe, and Daniel will be lined up to pose for a picture. How many poses are possible? So let's try this idea of thinking of blanks that we're filling in. See if this works. So we have 4 people, Anne, Brad, Chloe, and Daniel. And we're trying to line them up for a picture. For that first position on the left, any of the 4 people could be in that position. Now, once we've chosen one of the 4 people to stand in that first position, we can't choose that same person for the second position. So we only have 3 people left for the second position. And once we've chosen somebody for the second position, there's only 2 people left for the next position. And now we're down to only 1 person left to stand in the last position in the picture. So if we multiply those numbers, 4 times 3 times 2 times 1, there are 24 possible poses. Now, so far all we've done is count things. What happens if we want to determine a probability? So what's the probability that the pose will have Chloe in the leftmost position? Now keep in mind that probability has as its denominator the total number in the sample space, and that would be the 24. There are 24 total pictures we could possibly make ordering these 4 people. But now we need to find the number in the numerator. That would be the number of poses that will have Chloe in the leftmost position. So let's think of these blanks again. We want Chloe to be in the leftmost position. So there's only one way that can happen, and that is to put Chloe there. But once we've done that, there's 3 people left, Anne, Brad, and Daniel, that could go in the next position. And once we've chosen one of them, there's 2 people left for the next position, and finally only 1 person for the last position. If we multiply those numbers, we get 6. Now that's not a probability, but that's the number of poses there are that have Chloe in the leftmost position. The probability that Chloe's in the leftmost position is 6 divided by the total in the sample space, which is 24, or 1/4. How about this probability? What's the probability that the pose will have a boy in the leftmost position? So we already know the total in the sample space, that's a 24. We need to find the number of poses that have a boy in the leftmost position. So if we think about that leftmost position, it has to have a boy in it. That means either Brad or Daniel have to be in the leftmost position. There's 2 boys that we can choose from for the leftmost position. Now whoever goes there, whether it's Brad or Daniel, the other person now could go in the next position along with either of the 2 girls. So there's 3 people to choose from for the next position. And now we only have 2 left for the next position and 1 for the final position. 2 times 3 times 2 times 1 is 12. There's 12 ways we can put a boy in the leftmost position, so the probability that a boy is in the leftmost position is 12/24, which is 1/2. Here's another problem. How many license plates can be made if each plate must have 3 letters followed by 3 numbers? So let's imagine that we're making a license plate. The leftmost position has to have a letter in it, and there's 26 letters, so there's 26 possible selections we could make for the leftmost position. The next position also has to have a letter, so there's 26 letters we could choose from. The next position has to have a letter, there's 26 we could choose from. Now we have to have a number, there's 10 digits we can choose from. Then we need another number, and then another number. So if we multiply those numbers together, we get 17,576,000 possible license plates. How many of these license plates can be made if the letters and the numbers can't repeat? So we can still think about filling in our 6 blanks to represent our license plate. And we're still going to look at this position by position, but we have to think about the fact that we can't repeat the letters and we can't repeat the numbers. The first position is a letter, so there's 26 possible letters we could choose from. But whichever letter we choose from for the first position, we can't choose it again for the second position. So we only have 25 choices for the second position. And the third position can't be either one of those 2 letters, so we only have 24 letters to choose from. Now we're ready for some numbers. There's 10 numbers to choose from in the first position where we can put a number, but we don't want to repeat that number, so there's only 9 possible numbers for the next position, and we can't repeat either of those numbers, so there's 8 numbers possible for the last position on the plate. Multiply those together and we get 11,232,000 license plates. How many of the license plates can be made if the letters and the numbers can repeat, but the first letter must be a vowel and the last number must be even? So the first letter has to be a vowel. There are 5 vowels, A, E, I, O, and U. Any of those could be in the first position. The second position has to be a letter, and they can repeat, so we can choose any of the 26 letters for the second position. Third position could be any of the 26 letters. Fourth position, now we're having to choose a number, and the numbers can repeat, so we still have any of 10 digits left. But now for the last position, it says the last number has to be even. So it could either be a 0, a 2, a 4, a 6, or an 8. So there's only 5 numbers we can choose from for the last position. If we multiply those numbers together, we get 1,690,000 ways we can make this license plate. So let's keep talking about ordering things. How many unique orderings are there of the letters T-O-P? Now this ought to look kind of familiar. We started off by ordering the letters in the word act. That was 3 letters and we had 6 orderings, so we should get 6 orderings here. Let's see if we do. T-O-P, T-P-O, O-T-P, O-P-T, P-O-T, and PTO. So sure enough, there's our 6 orderings, 6 unique orderings. Those are all different words. Now remember, we can also find these orderings using factorials. So if we think about ordering 3 letters, there's 3 factorial or 6 ways to order these 3 letters. So what if we're trying to order the letters of the word tot, T-O-T? And what's interesting here is that we've got 2 T's, so if we try to order the letters in tot, how on earth can we tell the 2 T's apart? Well, we really can't, so just for now, let's go ahead and make one of the T's red so that we can tell them apart. So we've got this ordering, here's another ordering, there's a 3rd ordering, a 4th ordering, a 5th ordering, and there are 6 ways to order. The problem is some of these repeat. So we can tell them apart because we've colored the T's different colors, but really those 2 orderings are the same, and these are the same, and these are the same. So we've got some repetition, and the repetition's happening because some of the letters are exactly alike. So instead of having 6 ways to order, we've got repetitions of, well, everything repeats twice. T-O-T is twice, T-T-O is twice, O-T-T is twice. So we've really only got 3 ways to order. Now this is an example of something called permutation of like objects. The like objects here are the T's that repeat. We can make them look different in order to find orderings, but in reality, the T's look exactly the same, and because of that, we've got some repetitions that are happening by the orderings of the repeated letters. So let's talk about how we're going to deal with that. And let's look at an example to see how this works. When we're trying to permute, we're trying to order things that happen to have like objects in them. How many unique arrangements are there of the letters in the word pressures? So the first thing we're going to do is imagine that these letters are all different. There are 9 total letters, and if they were all different, we could order all 9 of them without any regard for any repetitions. But we do have 2 repeated R's, 2 repeated E's, and 3 repeated S's. Now if they were all different, there'd be 9 factorial ways to order the 9 letters. But we have some repetitions, so we're going to divide by the number of repetitions of these orderings that we have. If there's 2 repeated R's, there's 2 factorial repetitions of every word that has the R's reversed. If there's 2 repeated E's, there's 2 factorial repetitions of words that have the E's reversed. And if there's 3 repeated S's, there's 3 factorial repetitions that involve just reordering the S's. So we have to divide out by the number of repetitions we have. Now, in order to simplify this, we need to expand all of those factorials. So 9 factorial, 2 factorial, 2 factorial, and 3 factorial all need to be expanded. And then in order to evaluate this, we're just going to look for like factors. So I could say 2 times 1 times 2 times 1 is 4. And 3 times 2 times 1 is the same thing as 3 times 2 times 1, which leaves us with the 9 times 8 times 7 times 6 times 5, or 15,120 ways to order all of the letters in the word pressures, taking into account that we do have like objects. So what if we're arranging objects, but the order doesn't matter? Then we have something called a combination. And here's an example of a situation where order wouldn't make any difference. Laura needs to select any 2 of 3 essay questions to answer on a test. How many different selections can she make? So she might decide to answer questions A and B, or maybe questions A and C, or maybe questions B and C. And remember, the order makes absolutely no difference. She's simply selecting questions to answer. There's only 3 ways she can do that. Now that's because picking B and A is the same thing as picking A and B. She still answered the same 2 questions. Picking C and A is the same thing as answering A and C. The order doesn't make any difference. It's the same 2 questions. Same thing with C and B being the same thing as B and C. So that 3 factorial ways we would have to order the 3 questions, if order made a difference, is not actually what we're looking for here. We need to divide that by the number of repetitions we have where we're counting these orderings as being the same. For example, A and B is the same thing as B and A. A and C is the same thing as C and A. So how many of those repetitions of the same orderings do we have? Well, in this case, since there's 2 questions that we're choosing, there's 2 factorial orderings of those 2 questions. 3 factorial divided by 2 factorial is 3 times 2 times 1. 2 factorial is 2 times 1, and that simplifies to 3. So let's generalize this with a formula. The number of ways to choose R objects from N objects without order is a combination of N choose R, which is the permutation of R objects chosen from N objects divided by a permutation of R objects chosen from R objects. So let's look at an example of this. How many ways can you choose 3 books to buy from a list of the 10 best-selling books? Now, since it doesn't matter what order we choose the books in, we're going to be using a combination here. We are trying to choose 3 books out of 10 where order doesn't matter. Well, if order did matter, that would be a permutation of 10 choose 3, choosing 3 books out of 10. But order doesn't matter. That means we need to divide by all of the repetitions we have when we choose those objects with order. And since we're choosing 3 books, the number of repetitions is a permutation of 3 choose 3. If we expand those permutations and then simplify, we have 120 ways. A committee of 3 people is to be selected from a group of 4 women and 3 men. How many different committees are possible? Now, if you think about committees, people that sit on committees simply sit in a big group. There's no offices that are held. It's not like you have a president or a vice president. It's just a group of people. It doesn't matter what order those people are in. So this is a combination. And we have 7 people in all that we're trying to choose 3 people from for this committee. So we're looking for a combination of 7 choose 3. That's equal to a permutation of 7 choose 3. In other words, well, maybe order would make a difference when we choose these 3 people out of the 7, but then we say no, we're double counting, triple counting, actually over counting by this many times, a permutation of 3 choose 3. So we're going to divide through by all of the repetitions that we're counting over and over again. And if we expand each of these permutations and then simplify, we get 35 possible committees. What's the probability that the committee is made up of all women? So now we're back to probability. We need to think about the total in the sample space, which would be the total number of committees we can make. That's the 35, and that's our denominator. The numerator is the total number of committees that have women on them. So now we have to think about what we're doing to choose this committee with women on it. That means we would be choosing our 3 people for the committee out of only the women. So a combination of 4 choose 3 is a permutation of 4 choose 3 divided by a permutation of 3 choose 3, which is equal to 4 times 3 times 2 divided by 3 times 2 times 1, which is 4. So there's only 4 ways we can make a committee with all women, but we want to know the probability that the committee has all women on it. So we need to take that 4 and divide it by the 35 in the sample space to get the probability that the committee has all women. So now you've seen what permutations and combinations are. Permutations, remember, are number of ways to count objects when order does matter. Combinations are a number of ways to count objects when order does not matter. And we've seen how to use both of those in probability problems.